Every single smart device you own, your phone, your watch, even your car, is powered by these incredible little silicon chips. And they aren't just tiny parts. They're like these microscopic cities with billions of logical roads and buildings. But how on earth do you draw the map for a city that small? Well, it turns out you don't draw it. You write it in a very, very special kind of language. So today, let's dive into the language of circuits.
This question right here gets to the absolute heart of it all. We all kind of get software, right? It's a list of instructions. It tells a processor what to do step by step. But that's assuming the processor is already there. So how do you tell the raw silicon what to be in the first place? How do you describe the millions of physical gates and wires that have to be perfectly arranged to even create that processor from scratch?
To answer that, we have to jump into the world of hardware design. And let me tell you, it requires a completely different way of thinking than your typical software programming.
I love this comparison because it just clicks. Think about software like a recipe. You follow a sequence of steps, one after the other. First you do this, then you do that. But hardware, it's a full-blown orchestra. Inside a chip, literally millions of tiny components are all active at the exact same time, each one playing its specific part in perfect harmony.
And this whole idea has a name, concurrency. It's just the way the physical world works. And honestly, it's the secret sauce to hardware's incredible power. So it makes sense that any language we use to describe hardware has to be totally fluent in this kind of massive parallelism.
Okay, so take a look at this. We've got two separate adder circuits here. One's busy calculating A plus B, while the other is calculating C plus D. And since neither one needs the other's result to do its job, they can both just go for it at the exact same time. The results pop out in parallel. Easy. But of course, it's not always a free-for-all. In this example, the second adder is totally stuck. It can't start its work until it gets the result from the first one. It's just forced to wait. So this creates a sequence of operations. A real hardware language has to be able to describe both of these situations, the orchestra and the recipe.
So, the big question is, how do you write a language that can handle both of these realities at once? Well, engineers came up with a special class of languages just for this, hardware description languages, or HDLs for short.
Yeah, these are not your typical programming languages, not by a long shot. They have to describe the actual physics of the real world. That means they need a built-in concept of time and signal delays, because electricity is an instant. They have to figure out how to manage conflicts if two parts of a circuit try to drive the same wire. And they have to think in terms of individual bits and how they group together into bigger data pathways.
Now, while a lot of HDLs have been created over the years, one of them has emerged as the undisputed king of the industry. So it's time we talked about Verilog.
Verilog's story is pretty cool. It starts way back in 1983, where it was first built for simulation. Its name is actually a mix of verification and logic. But the real game changer came later, when tools were invented that could automatically translate Verilog code into what's called a netlist, which is basically a super detailed map of simple logic gates. All of a sudden, you could design with it. And once it was standardized in 1995, its dominance was pretty much a done deal. And just how dominant are we talking? Well, today, Verilog and its newer, souped-up version, System Verilog, are used in something like 80% of all digital chip designs. The message is loud and clear. If you want to design hardware, you learn Verilog. So why? Why did Verilog crush the competition? It really boils down to three key things. First, it was built for speed, which made simulations run really fast. Second, those automatic synthesis tools we talked about made it incredibly powerful. And third, and this was huge, it looked a lot like the C programming language, which meant a whole generation of engineers already felt right at home using it.
Okay, so we know why it's the king. Now let's get our hands a little dirty and see what the grammar of a circuit actually looks like when you write it down.
You know, this quote from Through the Looking Glass is just a perfect metaphor for this. When you're describing a physical object with nothing but text, there can be absolutely no room for confusion. Every single symbol has to have one and only one precise meaning. In the world of hardware, the language is the master. That's all.
Under the hood, a Verilog file is really just a stream of text, a lot like a C file. And just like C, it is case-sensitive. That means a lowercase data underscore bus is a completely different thing than an uppercase data underscore bus. That level of precision is absolutely non-negotiable.
And this need for precision gets really, really specific, even with something as simple as writing down a number. You can't just write 10 and call it a day. Nope. You have to specify everything about it. For example, 8HA1 is a complete definition. It tells the system, hey, this is an 8-bit number, it's in hexadecimal, and its value is A1. There is zero room for misinterpretation.
All right, now let's dig into the core building blocks Verilog uses to model this whole digital world: wires, variables, and vectors.
We've all been taught that digital logic is binary. It's all just zeros and ones, right? Simple. Well, when you're modeling real-world hardware, that's actually not quite enough. Verilog needs 4 distinct values to get the job done.
So you have your usual suspects, 0 for low and 1 for high. But then you have X, which means unknown. This is absolutely essential for simulations, like when a chip first powers on and its memory is just who knows. And then there's Z for high impedance. The best way to think about this is a wire that's completely disconnected, just floating, not being driven to either 0 or 1.
So, how do we actually use these 4 values? Well, in Verilog, everything is basically either a connection or a storage box. A wire is that connection. It just passes a signal along. It can't hold a value itself. A reg, on the other hand, is a storage box. It's like a tiny memory cell that remembers the last value you gave it. This difference between a simple connection and a storage element is one of the most fundamental concepts you have to get right.
And of course, we're rarely dealing with just one bit at a time. We group them into what we call vectors. So when you declare a wire 7:0 data bus, you're not creating one wire, you're creating a bundle of 8 wires, all neatly numbered 7 down to 0. This is how we build the wide pathways we need for things like memory addresses or sending a whole byte of data at once.
So, let's take a step back. We have concurrency, we have 4 different logic values, we have wires and vectors. When you put all these pieces of the language together, what do you actually have?
This is the incredible, almost magical power of an HTL. All of this precise grammar, all these rules, they are all designed for one purpose: to let an engineer take an idea from their mind, describe it perfectly in a text file, and then use automated tools to turn that text into a physical, functioning piece of silicon. It is literally turning language into reality.
You see, Verilog isn't just a programming language, it's a language for building reality. It's the blueprint for the entire digital world that surrounds every single one of us. So the only question left to ask is, what will you design?